Good morning or good afternoon, depending on where you are at. My name is Atarot Azizi Namini, Director of the IBT / ABCUTC. Very warm welcome to more than 900 sites that have registered to listen to our August 2025 monthly webinar. We are very delighted to have with us two very good speakers giving a talk on smarter steel bridge design to accelerate bridge project delivery. We have with us Frank Russo, founder and principal, Russo Structural Services, and Wayne Bartuka with Bridge Steel Specialist with National Steel Bridge Alliance of the AISC. During the registration process, we did receive a number of the questions, but it is not late. You can also submit additional question on the dashboard as the presentation is progressing. We also wanted to share with you just a couple of news about our upcoming conference. We hope to see many of you there. We hope that you will submit the abstract and participate. The 2026 World Bridge Engineering Conference, which is formerly known as formerly we called it the International Accelerated Bridge Construction, but since last conference in 2024, we have changed the name. It's called the World Bridge Engineering Conference because it covers much more than just ABC. We are now tasked by the US DOT to also address basically all the innovation that comes into bridge engineering. The conference is sponsored by US Department of Transportation through our University Transportation Center. And also we are delighted to tell you that our conference is also sponsored with the active participation of more than 33 state DOT engineers. You have a copy of all the presentations that are being made. If you go to our website, the deadline to submit the abstract is February 2026. So we hope that you will consider to, if you have interesting projects, to submit it online. It's very simple. You go to there's a QR code, and then if you scan it, you can submit your basically the abstract. There is also a possibility for exhibit. The space I can tell you is very limited. Already we have many exhibitors that have signed in. So please reserve your exhibit booth as soon as possible. Also, we have reserved a block of room at a special conference rate. December in Miami is a very popular place. The good news is that we have a block of room and a special conference room. We are also going to announce in our next monthly webinar award program. So there's going to be award program during the conference. So we will share more news on that next week. So at this time, I'm going to give the basically screen to Kathy.
Great, thank you, Atarot. My name is Kathy Kroll. I am the co-director of technology transfer at the IBT ABC UTC at Florida International University. We thank you all for joining us for today's 173rd webinar in our monthly webinar series. Before we get started, I'm going to share a few announcements with you. First is the 2025 Western Bridge Engineers Seminar that will be held in Tacoma, Washington on September 2nd through the 5th. So that's coming up really quick. Registration is open. Next, the PCI Prestressed Concrete Precast Prestressed Concrete Institute will be hosting the 2025 PCI Committee Days Conference from September 16th through the 20th in Chicago, Illinois. Registration is open. Next, AISC and SBA will be sponsoring Steel Days 2025. This is a nationwide event to be held October 20th through the 24th that offers steel enthusiasts, both young and not so young, opportunities to learn about careers in the steel industry. Next, the ASB, American Segmental Bridge Institute, will be holding their 37th annual convention in Bellevue, Washington, October 27th through the 29th. For all events, please follow the links that are on the screen. The next slide is a different type of announcement. We intend to share one interesting current piece of information from the bridge engineering industry each month. This month, we would like to point out one of the documents on the screen has been published by FHWA in July of 2025. A link is shown on the screen, or you can search the title, which is a framework for field inspection of in-service FRP reinforced strengthened concrete bridge elements. Our own FIU was the organization that performed the work for this document. The recommendations of the document were successfully balloted at the 2025 AASHTO-COBS annual meeting. Also note that this document was mentioned during and is directly related to our May 15th webinar titled Maine Builds FRP Tub Girders. The May 15th presentation can be found in our webinar archives for anyone who is interested and may have missed that webinar. Now for a few of our own IBT, ABC, UTC events. Our next monthly webinar will be held on Thursday, September 25th from 1 to 2:15 Eastern. Note that this is later in the month than our typical schedule to avoid conflicting with PCI committee days. The featured presentation will be in-service deck replacement at I-90 Columbia River Bridge in Vantage, Washington. Amy Leland and Anthony Mizumori from the Washington State DOT will be presenting. We're modifying our internal process a bit to allow for earlier registration for webinars. So you can see at the bottom of this, we usually say registration coming, but now we have our registration already open. So please go ahead and register for this conference, webinar immediately. Our last announcement is regarding our annual in-depth web training. As many of you know, each year our advisor committee selects a topic to provide more detailed coverage. Our topic for 2025 is Simple for Dead Load, Continuous for Live Load Steel Bridge Systems. We'll be learning about the history of this topic and how to design the system. We'll be presented with case studies by both Missouri and Nebraska, and we'll hear from the construction industry about fabrication and constructability. The next slide shows the agenda. The event is only 2 weeks out, so please register and get this event on your calendars. Registration is open. That's all for our announcements. On to our standard housekeeping items. As many of you may know, these webinars are recorded and posted on the IBT ABC UTC website in the section titled Monthly Webinar Archives. So you can access this and all previous webinars for future learning and to share with interested colleagues. I'd also like to point out that the PDF version of today's presentation is provided in the archives. Lastly, this presentation will be followed by approximately 15 minutes of question and answer. With that, we'll begin our featured presentation. I invite the presenters, Frank Russo, the founder and principal of Russo Structural Services, and Vin Bartuca, a steel bridge specialist with the National Steel Bridge Alliance. Both are renowned experts in the industry, and we're very fortunate to have them presenting today. Thank you both for sharing your time and expertise with us today. With that, we'll turn the screen controls over to Frank.
All right. Thanks for the introduction, Kathy. Let's go ahead and get started. You want to design a steel bridge, so let's talk about some of what is required. We have to lay out the spans. We have to figure out the beam spacing and overhang. We have to decide what kind of bracing we're going to use and what spacing. We have to do the nuts and bolts of sizing the webs and flanges and stiffeners and splices and shear connectors. And how about some other fun new things, like what about wind on the erected steel? Might we need lateral bracing? And is our span inherently stable? So we're going to talk about some of the AASHTO LRFD 10th edition stability checks that are new and are needed for deck casting. So what is bridge design? Well, bridge design is kind of a unique combination of shalls and musts. Those are the things we find in the specification. In the case of a highway bridge, that's going to be AASHTO. Some of the things you should do. Well, maybe you're going to find that in the commentary, the specification. How about some things that would be good if you did them? A good source of kind of standard industry guidance on best practices would be some of the National Steel Bridge Alliance or the NSBA's collaboration documents. How about I wish you would? Some other guidance. Maybe your local fabricators or erectors have preferences. And then there's don't you dare. And don't you dare the things that we have to avoid at all costs. I like to tell designers there are many good designs. We ought not argue about whose design's better. Maybe the thing we ought to do is avoid the bad ones. So that's what a bit of this presentation is about. I want to begin at the end, and that is to sort of tell you where we're headed or why we're making this presentation. It's to highlight for you some of what can be found in AISC's NSBA standard planes for steel bridges that you'll find at the homepage or the landing page of NSBA's website, which is highlighted for you at the top left of the slide there. The standard plans for steel bridges are going to be a series of PDFs of almost 300 pre-engineered bridges that you're going to be able to use to help you out with your design. As I said, there's nearly 300. If you want to count them, there's exactly 296. The spans range from 80 to 300 feet, beam spacings of 8, 10, 12, and 14 feet. And inside of the 4 PDFs, one for single span, one for 2, one for 3, and one for 4 span continuous bridges, you're going to find the girders, the stiffeners, the shear studs, the splices, tables of reactions and camber, pre-engineered diaphragms and cross frames, deck boring sequences, and even more. So let's begin by talking about kind of the fundamentals of bridge layout and planning in general, but also as it sets the stage for the various choices that were made in the development of the standards. If we think about continuous spans, we tend to favor what is known as a balanced span. So first of all, for multi-span bridges, continuous spans are generally preferred because they're more structurally efficient. And once you make a span structurally continuous, then we know that the ratio of the spans has very much to do with the forces that are going to develop in the individual spans. And a balanced span arrangement, if we can achieve it, is preferred. And a balanced span arrangement, as the bullet at the bottom of the slide says, is one in which the end span is somewhere on the range of 75 to 82% of the length of the center span. It would be good if, right? If there are no constraints on what your span lengths could be, then it would be nice to have a balanced span arrangement. What is this? Well, this is the positive and negative strength load envelope for one of the nearly 300 bridges that are designed in the standards. And I simply grabbed the strength one bending moment envelope to illustrate this point of a balanced span arrangement. You'll notice that the peak positive bending moments in all 4 of the spans are virtually equal, right? They all nearly touch that solid blue line at the top of the slide. And the negative bending moments over all 3 of the piers are also virtually equal. So what does that mean for us? Well, it means that instead of a 4-span bridge with many different field segments, all of which have to be individually designed, I have a 4-span bridge in which, in all reality, I just have 2 things to design. One positive moment section that gets repeated in 4 different spans, and one negative moment region that gets repeated over 3 of the piers. So we have optimized to the extent that we can the longitudinal layout of the bridge. And now how about the transverse cross section? Well, we have to support a certain number of lanes and shoulders and whatever the roadway engineers dictate the highway cross section to be, but we still have latitude and flexibility then in choosing the beam spacing. And picking the beam spacing is some balance between establishing an overhang and establishing a standard beam spacing. In the literature and in some NSBA guidance and guidance from Federal Highway Administration, you will see it cited that a beam spacing or an overhang, that's about 28 to 35% of the beam spacing results in the forces in the exterior girders, which also carry the barrier rail and have different live load distribution characteristics. The forces in the exterior and interior girders being about the same. If you don't want to remember 0.28 to 0.35, just keep it in your head that somewhere about a quarter to a third, right? This is not high precision work, but if you keep your overhang to say a quarter to the third of the beam spacing, you will result in all of the girders in the cross section having essentially the same design forces. Well, what is a practical beam spacing? Well, in some respects, just go out and use your eyeballs and look at some existing bridges. What do we see? We see lots of bridges with girder spacings of 8 to 10 feet. Everybody has these. They're, of course, practical. 12 feet's common, not as common. 14 feet historically was maybe thought to be a wide girder spacing, but is not so unique anymore. Greater than 14 feet is particularly rare, and it's limited by the deck designs. And for those reasons, the standard plans provide pre-engineered designs that are 8, 10, 12, and 14 feet on center. Some other things you as an engineer have to think about. Do you live in a region of the country where future deck replacement, complete full deck replacement, is to be contemplated or considered? If so, then you probably need a girder line down the middle of the bridge to accommodate half-width redecking. And also, how are your decks formed? There are some places around the country that use stay-in-place metal deck forms. Other use stay-in-place precast concrete planks. Others are still using strippable, removable lumber forms. Each one of those sort of has a practical limit to the maximum beam spacing. How deep should a girder be? AASHTO provides some suggestions, not a hard requirement, but those suggestions echo traditional historic practice, and that is L over 30 is the depth, minimum suggested depth of the plate girder alone for a simple span, and we can go a little bit shallower, 80% of L over 30 for continuous spans, because we get the benefit of structural continuity. And then how about the girder and the deck combined? Well, the girder and the deck combined, again, starting with simple spans, you generally don't want to be shallower than L over 25. I can also tell you don't need to go much deeper than that to get an economical section. And for continuous spans, again, we can be a little bit shallower, 80% of L over 25 of what's shown in the specifications. Once we get into final design, there are some musts. For instance, B over T ratios and width of flanges relative to web depth, and lateral moment of inertia and symmetry requirements between the flanges. So those are just things that sort of happen naturally in final design, but I do want to draw your attention to the suggestion that exists at the bottom of the slide, and that is that the width of the flange should never be less than 1/85th of the length of the field section. Why? It becomes incredibly hard to pick that girder up with a crane or put it on a truck and ship it if you have very narrow flanges relative to the length of the section. So that would be one of those, it would be good if you ought to do this kind of things, but it's not an absolute in the specifications. We have to brace our girders. We can brace girders with cross frames, and cross frame is the name that we give to something that looks like a truss, for instance, a K or an X frame, or we can also use a solid diaphragm, like you see at the right-hand slide of the screen. For straight bridges, there are really no as-designed forces in those cross frames. We design our girders with some presumptive load distribution factor that assigns load to the girder, but never really considers the overall behavior of the system. So what governs the size of this bracing? If there are no computed loads, the answer is you're soon going to find out. But what role does that bracing have? Stealing one of the illustrations from the LRFD specifications, we see that there is some relationship. And on the horizontal axis, we're going to plot the unbraced length, and on the vertical axis, we're going to present the lateral torsional buckling strength of the cross section. As that bracing gets closer together or further apart, it influences how much strength that girder has, and that's what's highlighted in the equation on the right-hand side of the screen. There is some permissible stress, some strength of the non-composite section that is related to the unbraced length. There are other loads that come into girder systems that are important, and again, were considered in the development of the standards, and I just draw your attention to one of those, and that is the influence of the torsional loads that come in from overhang brackets. Right? Our bridges commonly have some sort of a concrete overhang that is several feet, and maybe as importantly, that's what also supports the deck finishing machine, what we call the bidwell or the screed that rides out on a rail that's several feet from the girder, all of which produces torsion in the system, all of which pushes in on the bottom flange and pulls out on the top flange, creating what's known as flange lateral bending. That flange lateral bending is highlighted by this term FL, and that is one of the stresses that has to be considered in addition to primary bending as we're doing things like checking the strength of the girder at the constructability stage. These are not trivial loads. Again, they come from the deck weight and the form and the screed and the walkway, but these flange stresses in the lateral direction can be on the order of 10 to 15 KSI. And they are then additive to the stresses from the girder self-weight and the concrete that come from the deck casting process. All of this was considered for you in the development of the standards. So where are we? Well, we have a good design in the sense that we've laid out some reasonable spans, we picked some reasonable beam spacings, we have a girder that maybe is about the right depth, and all of this can be done with a line girder, and we can make sure that all of this satisfies AASHTO using for instance, NSBA's LRFD Simon program, which can design a line girder for you literally in just a few minutes. But are we done? Is that all the specification asks of us? That we pick a couple of variables, we type something into the program, and magically we're finished? I'm here to tell you that maybe unfortunately, or fortunately for you, you're here today to hear it. No, we're not done yet. There are some other things to think about, like wind loads and stability of the bridge during construction, and these new stability bracing requirements that I alluded to earlier that have come into the specifications with the 10th edition. The wind loads during construction come to us from a guide specification that AASHTO published in 2017. But if you dig into that specification, what you find is that these are really just strength design loads, right? What happens to the bridge in a hurricane? It doesn't really say much about how does the bridge behave under ambient winds, and is the bridge sort of fundamentally too flexible to even be built, right? Can we put people out there and walk around on the steel if the bridge is moving around 2 feet in a light breeze? The specifications don't really address that. What do the specifications do? Again, they mimic a strength design approach that we see for completed bridges in the LRFD specifications, and instead provide a series of coefficients and loads that are applied to girders, let's call it in the open framing condition. This process of wind load on the open framing was considered in the development of the standards, and there is some detailed notes and design criteria that were used for the design of those bridges. So what is an engineer supposed to do about the service load behavior? Well, the answer is it really depends on where you work. The state that I live in, Pennsylvania, my home state, Department of Transportation, PennDOT has had some criteria that, best of my recollection, has probably been around 20 years, that talks about loads that are to be looked at during construction of the steel bridge and making sure that the steel is not fundamentally too flexible in the lateral direction. And if it is, how do you stiffen it up? Either by making the girder stiffer or by adding lateral bracing. PennDOT has a standard called Bridge Design Standard 620M that you might look at if you're interested in some of that criteria. What do these wind loads do, whether they're service loads or strength level loads? Well, in the case of a single span, they bend a whole bunch of girders sideways. And we know what the moment is. The moment is easy, right? It's WL squared over 8. But even predicting the deflection gets a little bit challenging because we tend to not have a uniform moment of inertia down the length of our span, even in the lateral direction, right? We have smaller plates near the end of a span and bigger plates near the center of the span. So even predicting deflection is not so easy for a simple span. For a continuous span, this becomes a mess, right? There's not really any rational way to figure out what the moments or the deflections are because it depends on so many factors: the stiffness of the beams, the relative span length, the loads that are applied. But the good news is something like a grillage that you see here on the screen, or even just a line girder, right? Make one line girder, get the total result and sort of divide it evenly by the number of girders in the cross section, can be used to estimate those deflections and stresses. And it's just a reminder, right? Why do we care about these wind stresses? Well, during construction of the bridge, these wind stresses also become additive to, say, the self-weight of the structure. Again, as some sort of a strength or a service limit state check of the capacity of our flanges. It's not a hard thing to do, to go ahead and build a simple model and put some load on it. And at some point, you're going to find that your girder stiffness and your span length is such that maybe you do have excessive deflection. For instance, here is one of the many bridges that are in the standard plans for which I made these calculations. I applied the wind loads that come from that PennDOT design criteria, and I got 14.9, let's call it 15 inches of deflection at mid-span of, my best recollection is this was a single span bridge of 180-foot span. PennDOT has a criteria, again, that we sort of adopted in the development of the standards that said the maximum permissible deflection would be L over 150. So we're close, right? We're just a little bit over. Could we have closed our eyes to a half an inch? Probably. But the point I bring this up is to sort of emphasize to you, well, how do you get out of this problem? Well, one way out of the problem is just reproportion your flange. Take whatever the flange was, it was so wide and so thick, and just make it thinner and wider. When you do that, you increase the lateral moment of inertia, which is a cubic function of the flange width, and maybe that solves the problem. But at some point, you're going to run into potentially a span length or a bridge that's really high up in the air and has high wind loads on it, where you just can't rationally control the deflections anymore by tinkering with the flanges anymore. Your next solution would be to add lateral bracing. So this is to take that same exact bridge and just add lateral bracing at the end of the span. So you'll notice if you kind of stare at the image at the At the bay closest to us and furthest away from us, I have top flange lateral bracing shown in that model. The midspan deflections are now just a little over an inch. They were previously about 15 inches wide. Well, it's obviously we stiffened the end of the bridge. You know, it went from kind of a pinned condition to almost a fixed condition. And the unbraced length went from 180 feet down to 120. So all of those things tell you that that lateral bracing very effectively will reduce the deflections, but it's also going to pick up some load. And this is just an acknowledgement of a really handy design aid. So this lateral bracing now has some loads in it. How do I design this eccentrically loaded lateral bracing? I point you to a publication with a lot of really handy design charts from AISC's Engineering Journal from 2010 that talks about the strength of eccentrically loaded WTs. And all you do is go into one of these charts and say, what's my unbraced length and what WT am I thinking about using? And that table on the right-hand side of the screen tells you how many kips the member can carry. So there's not much you have to do other than go look something up in a table. Now, I had mentioned the stability design requirements, so let's spend a few minutes talking about that. What does bracing need to do, right? Every bridge we drive under, every steel bridge we drive under, if we look up, we see something called a diaphragm or a cross frame. Why did someone put that in? Well, I said earlier on that we put it in to reduce the unbraced length and control something called lateral torsional buckling. But it also would seem obvious if you think about it a little bit that we can't just put anything in there. We couldn't go get some drinking straws and put it in, and because it looked like an X or a K, consider it to be a brace. So obviously that brace has to have some minimum strength and some minimum stiffness in order to do its job. And I'm going to introduce you to the new provisions that have come into the LRFD specification in the 10th edition and sort of talk about very briefly what they do. The fundamental concept with something called a diaphragm or a cross frame is to prevent twist of the girder. Now, I've already said the word lateral torsional buckling a couple of times, and if we kind of slow it down even further, that means that the girder deflects laterally and it twists in the process of buckling. If I can prevent either one of those things from happening, then I can prevent lateral torsional buckling from being a governing design constraint. So the role of a diaphragm or a cross frame is not to prevent lateral movement, because we could push these girders sideways. The diaphragm or cross frame doesn't stop that. The diaphragm or cross frame stops the girder from twisting about its longitudinal axis. It prevents torsion. So that means that we can write an equation that says the torsional stiffness provided to the girder, the thing that stops it from twisting, has to be greater than or equal to some required amount of stiffness that the cross frame needs to have. So you're going to find in a brand new article in the specification 67422 these two following governing equations. They look a little bit messy, but on the left-hand side is stiffness, on the right-hand side is strength. What does the stiffness equation require us to do? Well, let's just take a look. In the numerators, the span length and the factor deck casting moment. So these are the moments that occur in the girder during the process of casting the deck. Given that we generally cast decks sequentially, particularly for longer span bridges, you've got to figure out the governing moments in the individual spans and use that as MU. In the denominator, we have E, we have the lateral moment of inertia of the girder, IY effective, and I have a little sketch at the bottom of the screen. It's the lateral stiffness of that girder, and it's just how many braces we have in the span. And then C sub B is a moment gradient modifier. So that's how stiff a cross frame needs to be. It has to be that stiff to stop the girder from twisting. If we acknowledge that no girder is ever erected absolutely plumb, that there is some potential sweep or twist in the girder, then that kind of becomes a seed deformation that also leads to a moment that will develop in the cross frame. So the equation on the right is everything in blue moved over. We're just going to bring the stiffness term over, and we're going to write that moment equals stiffness times displacement. What is the displacement? The displacement is a twist. The twist is L over 500, L being the cross frame spacing. So some lateral sweep of the flanges, top flange one direction, bottom flange another direction, over 500, and HO is the height of the girder. So it's essentially the angle in radians that forms by two flanges that are sweeping in opposite directions. And what are we trying to prevent? Well, what we're trying to prevent is an entire system from buckling. So this is a finite element model showing an entire system from failing because the cross frames were not stiff enough to restrain those girders from twisting and the entire system from failing and buckling. So what you're really seeing in the AASHTO LRFD specification in the 10th edition are sort of system buckling preventative equations. Now let's talk about what is the stiffness that's provided. What stiffness is provided to the girder or inherent in the system? Well, we have this equation in the specifications. It says the actual stiffness, and remember, the actual stiffness has to be greater than something that's required, is 1 over 3 fractions in the denominator. There's the stiffness provided by the cross frame or brace, that's beta BR. There's something called cross-sectional stiffness, which is beta sectional, and something called the in-plane girder stiffness called beta G. And if we go back to high school physics class, we'll realize that this is just a springs in series problem, right? 3 springs that are sort of strung together end to end. The total stiffness of that system is softer than even the stiffest spring because the springs are all leaning on each other for resistance. So let's start out with the cross frame. The picture on the left is a cross frame. The picture on the right is a cross frame. Were it not so silly, we would know that the one on the right doesn't work, but somewhere between paper towels and a steel cross frame is something that will be stiff enough to do the job. But how do we know, right? Where is that boundary that defines if some presumptive cross frame we're going to put in is stiff enough? Well, the specifications, we're going to start out talking about the stiffness of a cross frame. So the stiffness of the cross frame is simply the rotation that would develop. In this case, I'm showing you a truss. If we applied a moment to that truss, and the moment is sort of represented by equal and opposite forces acting at the top and bottom of the cross frame. The LRFD specifications are just going to give you the equation. So if you have an X frame, you simply plug in the areas of the diagonals and the chords and the height of the cross frame and the girder spacing into this equation, and it gives you the rotational stiffness of the frame itself. If you have a K frame, plug everything into this equation. If you have a solid diaphragm, then we're kind of back to moment distribution, fixed end moment, side sway kind of problem. What is the flexural stiffness of a beam bent in double curvature? It's just 6 EI over L. But these equations are given to you in the LRFD specification in these new stability articles. The cross-sectional stiffness is a term that frequently we're going to ignore, but what the cross-sectional stiffness says, and I've circled 2 pictures at the bottom of the screen for you. What if we had a cross frame that, for lack of a better word, let's say is shallow, meaning that there are large portions of the web above and below that cross frame, such that as the cross frame starts to develop force, the tops and bottoms of those webs, these sort of unbraced web sections, can distort. If our brace is less than 80% of the depth of the girder, then we have to think about this cross-sectional distortion, and there are equations given to compute it. But I want to remind you that for the most common thing we do, which is to design eye girders, specifications already require that a brace be 75% of the depth of the web. So if we have to be 75% of the depth of the web, and at 80%, we don't have to think about this cross-sectional distortion business at all. I'm going to tell you just go to 80% or taller and be done with it. And that's exactly what's done in the standard plans. And I've highlighted for you at the top of the screen, what are we talking about now? We're talking about the cross-sectional distortion term of this overall stiffness equation. And finally, we have what's known as beta G. If this bracing has a moment in it, then don't we agree that that moment gets transmitted as a force into the girders, or else where does it go, right? The system has to be in static equilibrium. So if I take end moments in the girders, and instead I convert them into shears acting up and down on 2 girders, like is shown on the right-hand side of the screen, I think you can see that what happens is we force a twist of the system. We force a deformation of the system. And when the specification gives you this equation for in-plane girder stiffness, this is the behavior they are talking about. The fact that there's an interaction between the bracing and the main girders that causes some roll and some deformation. And this is the equation you're going to find in the specifications. You compute this term capital NG, which is just a parameter about the number of girders in the system. and that gets fed into this term beta G, which then includes the girder spacing. Now the strong axis moment of inertia, because if you think about deflection and roll of that system, that has to do with Ix of the girder. And of course, the amount of deflection you're going to get has something to do with span length, and it's a span length cubed term in the denominator. So in summary, the specifications tell us that the actual stiffness that we provide, this springs in series stiffness of beta G of the girders, the maybe of the cross-section distortion, and the inherent stiffness of the cross frame has to be greater than some required stiffness so that system buckling can be prevented. In other words, lateral torsional buckling, this buckling between the cross frames, becomes the only thing that we have to think about once we provide minimum stiffness in our braced system. And a reminder again that the bracing has to have a certain amount of strength. So I took the equation from a few slides ago that was highlighted in some blues and yellows, and I just rewrote it here, and I put a K and a theta, right? Force is just equal to stiffness times displacement. So this moment, it's going to output some moment in inch kips or foot kips, right? Depending on what kind of units you use. And then there are these sketches on the right-hand side of my slide that show up in the LRFT specifications. And these sketches basically tell you if you have a moment, how do you turn it into forces in a cross frame? Well, you divide it by the height of the cross frame, and that gives you forces at the top and bottom nodes. And once you have the forces at the top and bottom nodes, and you know the slope of the diagonals, you can play method of joints or method of sections for a truss and get it all, or the specifications can just give you the equations, and that's what they've done. So this is how you get the minimum design forces in a cross frame in a straight bridge, for which you would otherwise not have any forces to design a cross frame. Summary. AASHTO now has some requirements in the 10th edition, requiring that flexural members be braced. The purpose of that stiffness is to control the twist in the girders. The restraint of that twist results in a force in the girder, so we have to do some strength design. But I'm here to give you some good news. In the development of the standard plans, there were about 200 unique designs of straight plate girder bridges with skews from 0 up to 20 degrees. And I'm going to tell you that typical cross frames designed just for KL over R to start with meet or come close to meeting the stiffness and strength requirements for every bridge that I designed. In no bridge that I designed did I have to come up with some unusual cross frame spacing or member size in order to get the cross frames to work. So yes, there's some new thing in the specifications. It's going to make us do some calculations. But if you find that unusual cross frames are coming out of your design, I would suggest that you go back and look at something. It's probably not the cross frame that's the problem. What if this doesn't work? And of course, there were some of my initial designs that didn't work, and I had to change some things. Well, the easy solution is to change your IY effective. Take your flanges, thin them out, and make them wider. You can deepen the girder to increase IX. You could add a line or two of bracing. That increases little n, which goes in the denominator of the stability equations. But if it's way off, then you're probably in the business of needing to add some top flange lateral bracing for 1 or 2 bays at the end of the span. Which end? The discontinuous ends. And then just a reminder, once you put this lateral bracing in, don't forget, it's going to grab all the wind load in the span, and that's where it's going to go. So you're going to have to design some things. So let's talk about now a tool that you can use that has everything that I've talked about it in, plus probably 50 more things I didn't talk about. And we're going to very quickly talk about the standard plans for steel bridges that I mentioned earlier, available on AISC's website. I was the lead designer. Russo Structural Services had this contract with AISC. Genesis Structures assisted us with some constructability advice and did the yeoman's work of doing a lot of the CAD work. And my friend Mike Grubb and I worked together on this pretty extensively, implementing all of AASHTO's new requirements, and then Mike going back and doing some quality control and AASHTO code compliance on the work. What are you going to find if you go to AISC's website? 4 PDFs. The single spans have designs in there for 8, 10, 12, and 14 feet on center. They have pre-engineered spans from 80 out to 300 feet in 10-foot increments. And it's not just the girders, it's everything else you see on the slide. Diaphragms, cross frames, lateral bracing if needed, fully designed field splices, deck details, link slabs. In total, all of this information is just 39 sheets of a PDF. For a 2-span, we're going to repeat the beam spacing. The span lengths that were chosen were 100 to 250 in 15-foot increments, and again with all of the supporting information. 3-span bridges and 4 spans happen to be the same, by the way. They are dictated by center spans that range from 150 to 300, again in 15-foot increments. The end spans were 78% of the span at center, which is kind of right in the sweet spot of the balanced span arrangement. All the supporting information, 33 sheets. 4-span bridges, all of the same information, 33 sheets. When you open the plans, you're going to see 8, 10, 12, and 14-foot cross sections. These are just the sketches of the cross sections. And I simply put in a box at the bottom of the page the ratio of the overhang to the beam spacing to show you that these are in keeping with the recommendation that I gave you earlier, which was like 1/4 to 1/3 or 0.28 to 0.35 rigorously. So that was 8, 10, 12. That was 8 foot, 10 foot. Here's 12 and 14 foot on center transverse cross sections. This was not just a design problem. There was a couple of month fabricator outreach at the beginning of the project where we talked to them about standard plate widths and web thicknesses and flange thicknesses and optimal web depths and stiffened versus unstiffened web designs for shear. You know, how do we optimize top and bottom flanges and how many complete joint penetration welds in a given field section? How long of a piece do they want to ship? How heavy of a piece do they want to ship? And then a whole bunch of other details about studs and splices and cross frames. So let's just show you what's in the standards. I'm just going to grab the 3 spans as an example of kind of the standard playbook that you see if you open the standard. So any particular piece of the standards kind of begins with a drawing that looks like this. You're going to see a typical section and you're going to see a girder elevation with just a whole bunch of variables all over it. All the plates, you're just given some letter of the alphabet name because you're going to be able to go look them up in a table. So as just a reminder, right, what's in the 3-span continuous standards, 8, 10, 12, and 14 feet on center, spans from 150 out to 300. You find a page of general notes. What do you find in the general notes? Well, lots of things. For instance, what loads were assumed in the development of the standard. So here's the non-composite dead loads, what was assumed for the weight of the forms and miscellaneous steel. What did we assume for the weight of railings? What did we assume for the weight of a future wearing surface? Design assumptions. This says, well, for girder design, we did all of these things. We used LRFD Simon, we designed for 20 degrees askew, we designed for infinite life, we did all of these things, right? So many, many notes that just talks about all of the assumptions in the development of the standards. A whole bunch of notes about wind load, because that was kind of a unique element of this project, right? We designed for wind, not just in the completed bridge, but in the erection condition. And these are all of the things that we assume. There's a whole table of flange lateral bending information. What did we assume for the weights of finishing machines? What were our controls on deflection and rotation of the girders during construction? So a bunch of notes, and then a bunch of charts that you can use that say if this is your web depth and this is your cross frame spacing, this is an estimate of flange lateral bending moment. Even if you wanted to use it outside of the standards, it's a nice way to help you with fascia girder design. Deck pouring sequences are given for all the continuous bridges, right? What did we pour first, second, third, fourth, and fifth, and why? And then I can also tell you that all of these decks were then also assumed to be poured from end to end continuously, and the design sort of envelopes the deck casting moments of either one of those scenarios. If we zoom in a little bit and say, pay attention to one of the pier sections, right? You'll zoom in and just see, as I was alluding to earlier, there aren't any dimensions given. It's all a bit cartoonish. And then just a bunch of labels. T is the top flange, B is the bottom flange. The segments all have a name, A, B, C, D. And what does that do? Well, it takes you to a table. So if you flip the page from the drawing we just saw, you're going to find a table that looks like this. We're going to zoom in to a piece of this table, and you're going to find, you know, a span configuration, and then just all the various plates. You know, for the webs, what's the height, what's the thickness, how long is the piece? For the flanges, what are the width, what are the thicknesses, what are the lengths of the pieces? For the various segments down the length of the bridge. A lot of times you're just going to see some tick marks, and that just means that the plate doesn't even exist in a particular design, right? It wasn't needed. For instance, the flanges, many times you'll see are just prismatic from end to end because the spans were such that introducing CJPs in the field section wouldn't make sense. Turn the page again, you're going to find a table with a whole bunch of charts on it. What are those charts? Well, here are all the transverse and bearing stiffeners for all of the potential spans. Here's the shear stud layout for all of the potential spans. Here is the cross frame spacing for the end span and the interior span. And on the right-hand side, what kind of braces used, a K, an X, or a diaphragm. Here are all the reactions, dead loads and live loads, both at the end, right, the discontinuous end, as well as at the interior continuous piers. And what are all the girder weights? I was talking to Vin a little bit before the presentation, and I wanted to remind him and remind you, in our interaction with the fabricators, one of the conclusions that we came to is we wouldn't have any field sections longer than 140 feet, and we wouldn't have any field segments heavier than 50 tons. And in the standard plans, you will occasionally see the use of high performance steel. That high performance steel was really in there only to make sure that we had field segments that were under the 50-ton limit. That's really what drove it. It's not that we couldn't have put in a really thick grade 50 flange, it's just that the segments got too heavy. There are tables of deflection and therefore camber information. And then all of the diaphragms and cross frames are pre-engineered. These tables will, for instance, tell you whether it's a diaphragm or a cross frame, whether it's a K frame or an X frame, and what size all of the chords and diagonals are. What are the sizes of all the welds at the heel and the toe, and how many bolts go in the connections at the top and bottom of the cross frame. So everything is completely designed for you. Again, sort of a cartoon or a picture of a bolted field splice with the top and bottom flanges shown at the top and bottom, the web in the middle. Again, a bunch of variables, some notes describing the various things that we assumed. And all those variables, of course, are key to a drawing, which has all the various plate sizes, the web plate sizes, the top and bottom plate sizes, fill plates if they're needed, and then how many bolts are in every connection are fully described in this table. And finally, pre-engineered slabs. So the pre-engineered slabs, this drawing happens to be for both for the simple spans and for the positive moment region of continuous spans. There is a companion drawing for the negative moment of continuous spans, and then one more drawing that shows where the additional, what we call the 1% rule, the 1% steel requirements, the additional longitudinal steel we put in slabs of continuous girder bridges. This shows where those terminations are, distance A and B into the two spans, and then the table just provides all of those dimensions for you. So conclusion, we have modern, cost-effective, and comprehensive standards that cover spans from 80 to 300 feet for simple spans as well as continuous spans. There are 4 unique beam spacings of 8, 10, 12, and 14 feet. Design of all of these beams was performed using LRFD Simon. There was extensive checking of stability during deck casting, stresses from the brackets, stresses and deflections under wind load all considered, and then lots of other things like splices and diaphragms and lateral bracing and shear connectors. It's pretty much everything you need for the design, other than you haven't stamped and sealed it and put it on a CAD sheet that's acceptable to your particular owner. I say the designs are near final. They only require adaptation to specific site requirements that may differ from the standards. That's it.
Thank you, Frank, for your presentation. My name is Vin Bartuka. I am the Steel Bridge Specialist with the National Steel Bridge Alliance. Today, I'll cover how the AISC NSBA standard plans, which Frank just discussed, can help speed up decisions, improve add value for both contractors and designers. So we'll start with design build and early decision tools. We'll move into type size, location studies, and the span to depth charts, some resources that Frank briefly touched on, some things that can be found or derived from the standards. And then we'll cover field splices and then conclude with the value that these resources can provide for contractors and designers. Again, these are all on our website, standard plans, and there's a QR code as well. So these tools give you a head start on deck sizing and bridge concepts. So time savings is something that we really want to stress that can help when you use these standards early on. By having a framework early, teams can then dedicate some resources to other innovations instead of reinventing the basics of bridge design. So type size and location Kickstarter, these standards really let you get into the scope of a project quickly. It reduces the risk of over and under designing, and it promotes collaboration. So as Frank famously has said in the past, these standards, they put you on third base with no outs. So close out a win without having to start from scratch. So you're on third base, these tools will get you to home. The span to depth charts are something that I'm planning on deriving from these standards, and they're shown as a steel girder depth over to the right and superstructure depth. These ratios can be used to quickly estimate the depth of the steel girder and the total superstructure. So this then can provide necessary vertical clearances, possible earthwork considerations, material shipping constraints, and erection feasibility. So some recommendations and considerations from my findings of these charts is that for steel girders up to 300 feet, ratios around 20 to 30 feet. So closer spacings allow for shallower girders. Longer spans may need deeper sections, and that's why Frank touched on the HPS 70, and thank you for covering that caveat about no field sections greater than 140 in these standards, and they're also no greater than 50 tons for lifting. So that's a very good point that Frank made. And then variable depth girders are also an option for optimization and aesthetics. Takeaways, this is a quick reference for girder sizing. It's not the exact bridge design as Frank pointed out, but it's a very close starting point, and it facilitates those checks, as I mentioned, is vertical clearance, some earthwork estimates, and shipping feasibilities. Next was the bolted splices. So you are able to standardize bolt quantities and sizes, which will then simplify constructability. So consistency across your projects reduces design effort and makes erection a lot more efficient. And lastly, some takeaways for contractors. Frank highlighted those girder weights, very useful for contractors for seeing improved fabrication, shipping, and erection efficiency. Designers can gain confidence in preliminary sizing because everything's there. And most importantly, both sides have a common reference points, which then promotes collaboration. So these standards are starting points for, but also a great way to collaborate. And thank you for your time. We're happy to answer any questions or dive deeper into any of the specific resources. There's my contact information, and again, available on AISC.org.
All right, thank you, Win, and thank you, Frank, for a great presentation. At this point, we're going to turn it to Paul Lives to moderate the question and answer period. Paul, it's all yours.
Okay, Atorid, thank you. We do have a few questions that came in beforehand and some during the question and answers. So with that, we'll go ahead and get underway. The first one I have here is one that came in earlier, and it just said, what is the practical shipping length that could be considered for a steel girder bridge?
I'll go ahead and grab it. As I mentioned, and Vin just alluded to, as we were developing the standards, of course, we had to pick some number. And in consultation with 9 different fabricators around the country, we concluded that with no other sort of extenuating circumstances, 140 feet was a reasonable length that each of them could fabricate and ship and generally deliver. And I can tell you that some of those fabricators were some of the biggest in the country, and some of them I would say are smaller and regional fabricators, and there wasn't really any daylight in the answer that they all came up with. right? So 140 feet and 50 tons was kind of the number. But I always say, you know, the actual site matters an awful lot, right? Is this a bridge that's going to be shipped into the mountains of West Virginia or Colorado and up and down twisty turny roads? Then maybe you're not getting 140 feet there. If it's being delivered out into the farmland, then, you know, maybe you can go 160 or 170. So the answer is, the engineer should probably understand a little bit about the nature of their site, but for the purposes of developing the standards, we picked a number that many fabricators felt comfortable with, 140 feet and 50 tons.
Okay, there's a question here about, could you comment on the effects of tariffs on steel bridges?
Sure, Frank, I'll take a stab at that one.
Yeah.
So for the most part, bridge work deals with Buy America, and tariffs don't directly impact prices of domestic steel. There has been some price increase in the last quarter, but it is not really directly impacted from tariffs. As I said, Buy America is a very strong program and allows for efficient pricing in the industry.
Okay. A question came in beforehand. Is there any consideration for in-service bridge inspection access in these methodologies?
There's not anything unique about in-service bridge inspection access in the sense like we didn't put a catwalk down the middle of the bridge or some kind of a thing like that. But I can say that, you know, in the world of things that are easy to inspect, you probably won't find anything easier than these bridges. They're very clean, very simple, steel plate eye girders with relatively few diaphragms and cross frames in them, right? So they would be accessible by all of your conventional means, right? Some sort of an underbridge snooper. These girders are not extra deep. There's nothing that is unique in any way about in-service and inspection of these bridges.
Okay. Here's another one. What degree of accuracy is there using a line girder analysis versus a finite element slab with girder elements analysis versus maybe an all plate element analysis?
Okay. So every one of those, of course, is going to give you a different answer. We could probably all sit around and argue amongst ourselves about who's right. I like to tell people in the end, we'd probably all be arguing about the wrong answers, right? So which flavor of the wrong answer do we want to feel is right? The sort of the origin of the live load distribution factor equations is that they were curve fits to finite element models that were made, granted, in the late 1980s and early 1990s when the distribution factor equations were developed, but they were purposely fit to have a very high correlation across a wide space to finite element models. So that's why we have so confidently designed girders with line girder for so long. I can tell you for a couple of the longer span bridges in this project, I did go and make some plate and eccentric beam models. And yes, the moments are a little bit different, sometimes a little bit higher and sometimes a little bit lower. And it depends on the particular girder and the particular span and everything else. But I never saw anything that would lead me to have a lack of confidence in traditional line girder analysis, which I would still endorse as the way we ought to be designing these kinds of bridges.
Okay. Another one here is, what is the single most challenging fabrication component in bridge systems, and can 3D printing help? The person that asked this said they were really interested in delays, I guess, mitigating delays.
Well, I'll talk about these bridges in particular, right? Again, we're talking about steel plate girders with just diaphragms or cross frames in them. Hearing fabricators talk for many years, they will sort of universally tell you that the girder is the easy part of the fabrication process and the cross frame is the more expensive and time consuming part of the process, right? It's on a per pound basis, it's like, 10 to 1, the cost of a cross frame relative to the girder. So, to answer in the context of these standards, the cross frame will be the greater aggravation, say, for the fabricator than making the girder, which is why there were great lengths taken to minimize the number of cross frames in these designs, simplify them to just use angles instead of WTs, and use very simple welded and bolted details, right? To the extent that we have to have some of these pain points in the fabrication process, let's make them as simple as clean as possible. Do I believe that any of those set themselves up for 3D fabrication? No, I don't. Right? 3D fabrication, the bridge fabrication industry is probably going to find its home in more complex elements. You know, complex nodes and trusses, complex nodes and arches, weird things that might be needed for rehab. I don't see any use of 3D printing of steel and eye girders and cross frames at any point in my career.
Okay. Person wrote in and said they were interested in the design of curved bridges and if the AASHTO 2024 stability criteria are applied in your material.
Okay, good question. So in the design of let's back up. The reason that the stability design criteria came into place is there was a thought that there were no rules that applied to the design of a diaphragm or a cross frame for a straight bridge. Because we designed straight bridges with a line girder, and because we designed straight bridges with a line girder, we have no way of getting any forces in these cross frames. So what do we design them for? So this stability design criteria was put in place to give us some mechanism to make sure that diaphragms and cross frames met some minimum requirements absent any system analysis. When you get into the design of curved girder bridges, those diaphragms and cross frames are going to have non-trivial forces in them just because of the role that they play in sort of linking the structure together in a 3D world, and those become the governing forces. Yes, you can do a stability analysis of a curved girder bridge because you're probably having to do that in some sort of a finite element model anyhow. So checking of stability would probably be easier done with the model that you already had. These equations were never developed to have some sort of a secondary or surrogate use in curved girders. They were explicitly set up for straight girder bridges.
Okay. Next one is, what is the most popular reinforced concrete deck construction system used in the USA?
Cast in place concrete deck with 2 layers of top rebar and 2 layers of bottom rebar, right? You know, and those decks are going to vary from, say, 8 inches thick. I mean, there are some people with a little bit shallower. I'll again sort of reflect on what's in the standards. The standards use an 8-inch thick cast in place concrete deck for the 8-foot girder spacings. When we go to 10 feet, it was 9 inches, 12 feet's 9.5, 14. So they were just traditional cast in place reinforced concrete slabs. As to how they are built, that varies around the country, right? My home state of Pennsylvania, again, I can go around and see stay in place metal forms all over the place. If we go to a place like Texas, it's a lot of stay in place, precast, pre-tension concrete, you know, subdeck panels or planks. And I used to work for the Iowa Department of Transportation many, many years ago, and Iowa was, and I still believe is, a strippable lumber form state, right? So there's, you know, different people have different ways of constructing the deck, but in the end, it's a piece of reinforced concrete with number 5s and 6s top and bottom in 2 directions.
Okay. What is the most common painting system used in the United States?
Ben, I don't know if you have any data from NSBA on the most common painting system. I mean, I'll say a few things to start off with. The standards were developed based on uncoated weathering steel, and uncoated weathering steel, you know, when the climate is right and the conditions are right, continues to be the most cost-effective method of fabricating, erecting, and maintaining for a long term steel bridges. The most common, you know, still seems to be some sort of a 3-coat paint system, right? With a primer, an intermediate coat, and a top coat, and the chemistry of those systems, whether they are organic or inorganic, tends to vary around the country and has to do with available moisture in the air and curing practices. So I don't know if there's anything else that you want to add, Vin.
Yeah, just to add that the most common paint system is a 3-coat polyurethane. but we are looking into different avenues and trying to steer the industry to use a two-paint coat system. Also, maybe I could touch on cross frames in general. Galvanizing those instead of painting could save time as well, because it could be very time consuming for the service prep of cross frames if they were to be metallized or painted. So galvanizing is a way to go there.
That's right. Yeah, if there's a decision that drives you away from uncoated weathering seal and you decide you need some corrosion protection system, the thought process is to just fabricate all the cross frames, send them someplace to get them dipped, and ship them to the site, and then do whatever you have to do with the girders. But painting of the cross frames is very, very time consuming.
And our uncoated weathering steel resource is a great resource on our website, so be sure to check that out for different procedures and recommendations.
Okay, one more. Can you comment on the use of cross frames if one uses ABC, accelerated bridge construction?
So I think what maybe I'm going to infer what I think the question is all about, right? That the users may be thinking about some prefabricated bridge units, that are going to come out with 2 girders in a deck and put them down to another unit, 2 girders in a deck, and that sort of thing. You're going to need cross frames in between the 2 girders just to get the deck cast even in the yard, right? The yard, wherever these things are going to be prefabricated, is going to need a cross frame. So maybe, again, I'm just sort of speculating what the question is. Maybe the user is asking, do I need to put diaphragms or cross frames in between the units, right? The bay that's going to get the closure pour, essentially, to link them together. Once you start leaving diaphragms and cross frames out of bays entirely, I suspect somebody's going to start to ask a question about live load distribution and live load distribution factors and methods. The reality is that most live load distribution happens through the deck anyhow, that the diaphragm or cross frame in particular in a straight bridge doesn't play a profound role. But I think people would start at least asking you to prove something or would ask a question. So, it's not a surprise that you would still see some sort of bracing put in between those girders. Now, the question is, does it need to be a full diaphragm or cross frame, or could be something as simple as a lean-on bracing? And lean-on bracing might be the most effective thing to do in those closure bays. And again, I would sort of point you to an NSBA reference on the design of lean-on bracing that you can find on the same website as the standards and the uncoated weathering steel guides and other things that Vin alluded to.
Do you superimpose the net bracing forces, the total, in load combinations with wind, seismic, etc.? I typically do, but some don't. So I'm curious what standard practice is with bridge designers.
Yes, you would. And there's sort of 2 pieces of it. The bracing design is predicated on the fact that the forces that are being considered are the deck casting forces. So you have to think, well, we're not casting the bridge in a tornado, right? So you're going to have very light to moderate winds that would be acting concurrently. You decide what wind you want to put, what ambient wind you want to consider, some 15 or 20 mile an hour wind, which is kind of everybody's cutoff for deck casting. And that's going to generate, a virtually zero wind force in any diaphragm or cross frame. So, is the technical answer is yes, but given that the stability bracing, stiffness, and forces are predicated on the deck casting, the concurrent wind is so small that it's not going to matter.
Next question is, my professor advises against using double angles for bracing. If you agree with this statement, can you please elaborate why? Otherwise, what sections to use for cross frame bracing?
Your professor is a very knowledgeable person and should be commended. The challenge of double angles for bracing, say, you see my screen, Ken?
Yes.
My screen still visible? All right. So let's go to this picture. And this brace on the left-hand side of the screen is what we call a K-frame, and that's made out of one angle welded to one side of the plate. If these became double angles, then that means we have to do a whole bunch of welding for angles on the front side and then flip this whole thing over and weld a whole bunch of angles on the back side. And as messy as that sounds, imagine then if the owner also said that that cross frame needed to be painted. Well, how am I going to paint in that little space in between the angles? Or how am I going to repaint it in 50 years when the paint has to be renewed? So things like, back-to-back angles are sort of strongly discouraged. And again, in the context of these standards, which are straight bridges with little to up to 20 degrees askew, there's no technical justification for any sort of a goofy cross frame or anything with double angles. Everything that is in the standards are all relatively small angles and they're all single-sided.
Great. Couple more questions and then we'll wrap here by 1:20 or rather 2:20. The concrete industry moves pieces longer than 160 feet. Why does the steel industry limit to 140?
Steel industry moves pieces as long as 160 feet or longer all the time as well, right? So the decision as to cut things off at 140 was simply for the purposes of establishing some dimensions so that a standard plane could be developed. It doesn't mean that someone can't move a piece longer than 140 feet. Steel girders longer than 140 feet get fabricated and moved commonly, but they require some coordination as the design of the project is going on to make sure you can really get something there.
Then did you have some more to add on that?
Yeah, just to add, there may be extra permitting required, but I always recommend reaching out to your local fabricator to discuss piece lengths as well and delivery routes. It's just a great conversation starter. Speaking to your local fabricator can sort out any shipping constraints, but just to add to that great point that we do ship commonly over 160, just these standards were with the fabricator's input for 140.
Great. And I'll add just a little bit to that too. Ben mentioned finding your local fabricators. NSBA is a fantastic resource for that. So go to the AISC, NSBA websites, contact your regional rep, and they can hook you up with the local fabricators. So,
yeah.
Frank, did you have more to add there, or?
I think all I was going to say is, look, as an experienced bridge designer, I've designed a lot of concrete bridges as well. I wouldn't want to make the tacit assumption that I could get 180 foot of anything anywhere, right? You start pushing into these longer lengths, regardless of what the material is, you simply have to do your due diligence during preliminary bridge planning to find out if it's possible. You just can't standardize around somebody thinking they can get 180 feet anywhere.
Great. We have had so many questions come in. It's great to have so much interaction from the audience. So Frank and Ben have committed to, we download all of the questions that come in. So we'll put those in a spreadsheet. Frank and Ben will go ahead and respond to all of those. So if we weren't able to get to your question today, please check back in a couple, 3 or 4 days, and we'll have those answers posted in the archives on the website. So with that, we'll go ahead and wrap up. Atorad?
All right, thank you. Thank you, Frank. Thank you, Win. Very informative presentation.
Thank you.
And thanks for agreeing to provide the answer to questions that we didn't get the time to answer. So also, I wanted just to, again, mention again the deadline for submitting the abstract for the 2026 World Bridge Engineering Conference is February 20, 2026. We hope that you will consider, if you have an exciting project, to submit an abstract to the conference. And more importantly, mark your calendar, please, and try to attend. Also, I want to just do one more time. It's coming up, actually September 9, very interesting annual in-depth web training that is going to be related to simple for dead load, continuous for live load, steel bridge system. State of the Missouri has done some wonderful job in the last couple of years. They have actually, the number of the bridges that have used the STCL in service and the ones that are planned to be designed and constructed altogether are going to be more than 60 some numbers. So don't miss our annual in-depth web training. That's going to be in September 9. It's a bit longer, from 11 to 3:15, but we dive into very detailed aspect of this system, which is very economical. So on that note, we will conclude our August 2025 webinar. In the total, the last count was 932 sites that's registered to listen to us live. So on that note, we will end the webinar so long, and we hope to see you in our next event. Thank you.